Alright, well, let's get started with chapter 13. This chapter is about some special structures that we can use in with pointers. We can create some more elaborate structures that will allow us to do useful things. So let's open up chapter 13, and the first topic is about nodes and linked lists. When we've looked at dynamic variables before, we looked at simple dynamic variables, primitive dynamic variables of single types. Those aren't really used a lot in the real world because it's just as easy to use simple ordinary variables that don't need any dynamic aspect. We added arrays because arrays are more useful, since we can make different size arrays based on the needs of the current run of the program, rather than having to worry about what the need is up front, not having to know what is going to be needed for each run of the program. And this chapter is talking about some more special types of dynamic variables that are interdependent structures. In other words, they connect multiple dynamic variables together. And we call the individual pieces nodes. Similar to the way the individual computers in a network are nodes, and they're useful in a similar way because they connect to the other nodes, and each node has some particular data that it holds on to. On page 723 we have a diagram representing a linked list. There's a head pointer that points to the top of the list. It contains some data, in this case roles, and a count of 10. The structure that they're using is listed there as well. Item, count, and link. So the item is roles, the count is 10, and it links to the next node in the list, which has jam 3, and a link to the next list, which is T 2, and an end marker. And typically the end marker is going to be a null. Practically, a null is going to hold a 0, but 0 is not generally considered a valid address. So we use that as a marker for the end of a list. There's a predefined constant null called so that we can use that whenever we need to set a pointer to null. That indicates we can test for that null value to make sure so that we know that that pointer is not pointing to anything. Okay, so that's a simple linked list.
So where's the null at?
Where is null defined? Or where do we use null?
Well, yeah, where I mean, kind of where, like in that one right there, where would you see it at?
Well, in that first example on page 723 where it says end marker, that would be the null.
Okay.
There's also a special operator that we can use with a pointer to make it easier to use members of a struct or class, and that's the arrow operator, dash greater than. It's the equivalent of a dereference and a dot operator, so that we can look at the contents of that particular element.
So is this gonna always be like a structure, basically?
Yeah, that's typically how it's going to work. It'll either be a structure. Basically, it's a list of structures. Each node is a structure that contains the particular pieces of data that we're holding on to for the members of the list. It can also be with a class, though, so if you could have the same type of list for a number of objects, so that we can those objects can then be accessed with their member functions and so forth. Okay. And then they talk more about linked list on page 728. They talk about making code for inserting a node at the head of the list. So head insert function. For adding a node to the middle of a list, a linked list. That's on page 730, 731. And that's what they're showing here. Oh, the head of a linked list is shown in display 13.4, which is what I've got up here. So the head insert basically we've got a pointer to the head and a value for the contents that we're wanting to add to our linked list. We create a new node that we then point to, and we put the value that we're wanting to store in the data part of that node. So these nodes only have two elements, a link and data. There's the structure. Okay, we then make the link for that new node that we just created point to the current head, and we make the head pointer point to our new node that we just created. So that's how you insert a node into the head of a linked list. All right. Um, so you want to be careful about when you're working with a linked list not to lose nodes. So for example, if we, instead of having a temp pointer, we just said head equals new node and put our data in it, and we had previously been pointing to one or more nodes, we would now no longer be pointing to those, and those would be lost out there in memory somewhere. Although still allocated, we have no way of getting them back and putting them back into the free store, the heap. And that's one way that memory leaks happen. A program just keeps getting bigger and bigger because rather than managing nodes of data effectively, they are losing them. Okay, the next section tells us about searching a linked list. And basically, searching a linked list involves making a temporary pointer that we can start at the beginning of our linked list and iterate through it. So here's the code from 13.7. So our pointer is here. We've initially set it equal to the head. If here equals null, that meaning head pointed to null, that means that the list was empty. So we can just return a null. Otherwise, we check the data in the current node, here data, for being equal to our target that we're searching for. And if it is, and the if it's not equal, then we go ahead and link to the next address. So we're searching through. As long as we don't find our target, we'll just keep linking unless our link is null. If our once we finish our search, meaning we either found our target or we hit a null link, then we check to see if it's equal to the target, in which case we return our current pointer, otherwise we return null. We didn't find it. That makes sense? You understand why that's how you would search through a linked list?
Kind of. Seems kind of complicated though.
Well, it's a it's another new concept. We're trying to deal with a large collection of data that it's in a particular order, and we search through it by iterating through the links. We follow the links to find the data.
So, how can I be sure that I'm creating one, a linked list? I mean, is there like certain syntax or like certain, I mean, are you gonna always use a pointer?
Basically, what happens is you the thing that makes it a linked list is the fact that you're creating nodes and you're linking to them. So basically, it has to have some kind of structure. You have to have multiple elements because one of the elements is the link to the next node. Does that make sense? So the minimum size for a linked list element is some kind of data and a link to the next element. Once you've created one, it may make it a little easier. Let's go ahead and look at adding a node to the middle, which is display 13.9. Again, we have the simplest node, data and a link, and we have a node pointer type def. So that's a pointer to a node structure. And you'll notice our node has a node pointer to point to the next element. Here's the insert function. In this case, we're using after me. After me is going to be the link or the element of the list that we want to insert our new data after. So we make a temporary node pointer, create a new node, put the data into the new node, we make our link point to the link from the after me element. So in other words, whatever came after me before will now come after the new element we just created. And then we make the after me node link to the new element we just created, the new node. And they've got a picture on page 737 that illustrates that. So they created a new node that's represented by 5 here. Temp pointer is pointing to it. They then made the new node point to whatever after me was pointing to before, which is represented by the node with the 9 in it. And then they changed the pointer for the after me node, which has the 3 in it, to point to the new node we just created, which has the 5 in it. So that's inserted. That's what that code does. And then finally, they show you how to remove a node. And that is illustrated in display 13.10. They didn't give us a code file for that. But basically what they do is they find the node that's pointing to the one we want to get rid of, and we point it to the one after the one we want to get rid of, and then we delete the one that we no longer need. Display 1313 is the interface file for a node class. They've created a node class. And that's, again, well, this would be about the simplest type of linked list that we could create in class form. All the data that it contains is an integer and a link. But they've got a default constructor, a node constructor with a place to hold a value, and they link to the next node. We can get the data for a particular node. We can get the link for the next node in the list. We can set the data or set the link. 13.14 is the implementation file. So the default constructor just creates a node with a 0 data and a null link. And you see the various pieces of the node class. We can make more complex linked lists. For example, a double linked list would have a forward link and a reverse link. So we'd be able to go from the front to the back, or top to the bottom, or from the back to the front, from the bottom to the top. So in order to do that, you would need, in addition to your data, a forward link and a backward link. Another kind of linked list that we could make would be a binary tree, which basically has a left link and a right link. Page 743 shows a binary tree that puts numbers into ascending order by using either the left link or the right link. And that's binary trees are used fairly commonly, particularly in graphics engines and game engines as an efficient storage mechanism for data that can grow and shrink rapidly over time. We talked about the interface and the implementation of a node class for a linked list. 13.15 is a program that uses the node class to create a list of nodes. So basically, what this program is doing is inserting the numbers 0 through 4 one at a time at the head of a linked list. They will end up in reversed order because as we add a new head, we push down everything else. So 0 starts out at the head, and then 1 becomes the head with 0 after it, and then 2 becomes the head with 1 and 0 after it, and so forth. And then, so once we've inserted all the numbers from 0 to 4, we iterate through the list and spit them back out. And then they delete each node from the list one at a time. Okay, so now you've got all of the basic methods for dealing with lists of nodes. Let's look at a couple of practical implementations of what we can do with those. One of those is called a stack. You may have heard of a stack before. A stack is pretty commonly used in programming and in operating systems. So what actually happens when your program calls a function that calls another function that calls another function, the current operating system environment gets pushed on the stack, and the deeper you go, the further down the stack gets pushed. If you look at the diagram at the bottom of page 747, you'll see they pushed A onto the stack, and then B, and then C. So if A was your main function, then B would be a second function that you called, and C would be a third function. And from C we called a fourth function. Then when we return back from the fourth function, it would get the information from the stack to go back to where it was executing in C. When it ended C, it would go back to the information that it stored for B, and so forth. So stack is a way to do a last in, first out type structure. The last thing you put in there is the first thing you take back off. And a stack, this implementation of a stack is pretty typical. We've got a push to put something on the top of the stack, a pop to take something off the top of the stack, We can check to see if the stack is empty or not. And when we're done with the stack, we can destroy it with the destructor. Yeah, we've got a constructor and a destructor. And here's a short program that they wrote to use the stack class. You enter a word, it pushes each letter of the word onto the stack, and then pops them back off again to read the word back out backwards. Okay, another, well, and here's the implementation of the stack, so you can see what the push and pop look like. Another structure that is used fairly commonly in data structures and computers is a queue. So queue is a first in, first out data structure. And so basically we want all of our things that we're processing to be first come, first serve, like the line at the bank. If you have a single queue at your bank, we always know that the first person that came in is the first person that's going to be helped. This would be similar to how input data is handled in a program. So the first event that happens is the first one that gets serviced. So 13.21 here is the interface file for a queue. And 13.22 shows us a sample of using a queue. We add things to the queue and then remove things from the queue. Things that we add stack up in order. When we remove them, we remove the next element off the front of the queue. And 13.23 shows you the queue implementation. So, any questions about pointers, linked lists, stacks, queues?
So the arrow, I'm just trying to figure that out. Starting to kind of figure out, I guess, how you create. So the arrow operator is that going to be? Let me see. Okay, yeah, so it's a pointer It allows a pointer to point to the member variable of the linked list.
Yeah, basically, it's if it, the pointer operator, that's the dash greater than symbol, that we call that the arrow operator, and that is the equivalent of a dereferencing operator combined with a dot operator. So we're dereferencing the member of that structure that's pointed to by the arrow. Does that make sense?
Yeah, kind
All right, so our assignment this week is going to be number 6, project number 6, which is about the suitors for Princess Eve. Okay, so basically what happens is all of the suitors are lined up and they're assigned numbers, and Eve counts down 3 suitors, and the 3rd suitor gets eliminated. And she keeps doing that, always counting to 3, and when she gets to the end, continuing back at the beginning until the last suitor remains standing, and that's the one she's going to choose. So your assignment is to create a circular linked list. Basically, that's a linked list in which the tail or back of the queue points back to the front of the queue. Allow the user to specify how many suitors are in line, and tell me who the winning suitor is using that elimination method. Okay, does that make sense?
of. Yeah, sounds pretty difficult.
All right, well, how do you suppose you would get started?
Well, you need to create the list.
All right, well, the simplest way to do that would be to start with a node like we had in display 13.9. So this one, it shows you how to add a node in the middle of your list. Let me go back. .7 shows us how to locate a node in a linked list. .4 shows us how to insert a new node into a list. So basically what you're going to need to do is, starting with the number of suitors you had, so in the example there are 6, you would create a new node for each suitor. So just for the heck of it, let's start with this code. And I'll copy it into my main code window here. So how would you create the linked list of suitors based on the number of suitors given by the user?
We're trying to do what?
So the user is going to give you a number. They have an example using the number 6 on page 764. So once the user has given you that number, in order to solve this problem using a circular linked list, we have to create a circular linked list. So how would you create a circular linked list with 6 elements numbered from 1 to 6?
So the user says 6, and we just need 6 elements.
Yeah. So the user says 6, we need 6 elements. If the user said 145, we would need 145 nodes. If the user said 1216, we would need 1216 nodes. So whatever the number the user enters, you need to make a linked list with that many elements in it. And it needs to be a circular linked list. So how would you do that?
I'm not too sure. Did you implement like a queue into it? Maybe?
Well, a queue is just a specialized type of linked list that is intended to be accessed by retrieving first the first element that was put into it. So probably a queue, you could make a queue work for this, but it would be a little more complex than you actually need for this problem. We don't technically need to create a class and make an object or make objects to implement the linked list for this problem. We can just use a simple structure as long as we link everything together properly. So how would you create a one element linked list, a one node linked list?
You could just, I guess if you were starting from there, you would just go node pointer, and then I guess just give it a name.
Okay, what would you call it?
I don't know, item, I guess, something like that.
Okay. Then what?
And then I believe you would go item equals new node.
Okay. And then?
So, have we not created the node yet?
We've created it, but we haven't put data into it yet. It's empty. So an empty node is a useless node.
So item is the pointer, right?
Yes. It's pointing to the new structure that we allocated in memory.
So we could go item points to data. And then give it, assign it, I guess, a value.
Okay.
So that value that we assign, is that going to be, is that like how many elements?
Well, it's going to be the position of this particular element in our list of suitors. So the first element would be,
Is this zero indexed or not? I don't.
well, in this case, the
It doesn't
suitors
have
are
to be.
numbered starting with 1, so it would be
Start with
1,
one. Stick with one.
right. So suitor 1 has the data 1. And what else do we need in our new node?
Do we need the null?
Like,
Item equals the link equals null.
like that? I would say that would be appropriate for a regular linked list. What we're trying to do is make a circular linked list, so the last element should link back to the first element. So how would we do that?
Should it equal 6?
I'm sorry, what equals which?
Should it equal 6? Maybe?
Okay, what is 6?
Well, I thought that would be the last element. So,
Okay, that's the data that goes in the last element.
uh,
So let's go back a little bit and think about this from the point of view that of the problem we're trying to solve. So what is our input?
the number of suitors.
The number of suitors, okay. And what is our output?
Uh, our output should be one through six, I guess.
It's going to be something between 1 and 6. It's going to be the position of the suitor that gets to marry the princess, according to our algorithm.
Okay, so whatever, because she counts 3 suitors in.
She's going to count 3 suitors and eliminate that suitor, so we're going to need to be able to eliminate nodes from our list. But first, we need to be able to create our list based on the number that the user types in. So we need to make some generic code that will allow us to make any size list of suitors. So we've made some code to make a 1 item list. I would say the last one should not be null. It should point to the first one, which in this case is also the first one. I would say we probably need to have something to hold on to the head of the list. Okay. Something like that, maybe. And So item, the first node should have data 1 and it should point back to the head. But then if we add another one, it should have data 2 and 1 should point to 2. Does that make sense? So basically we need some way to add a new item onto the end of our list now. So we could make that its own function. Basically we'd take the current item and add a new item after it. We had some code to do that. Do you remember what that code was in? Here's a code to locate a node. Here's a code to add a node in the middle of a linked list, the insert code. So basically we could just copy this insert code and we could say insert item 2 to make the second node, right? And that would automatically link the first node to this node and link this new node to whatever the first node was linked to before. Does that make sense?
Yeah.
So, presumably, okay, I could link 6 items together like that. Now that's not the most efficient way to do it. Not what I'm recommending for you to do. But that's an example of some code that would work. Once you have a linked list of the appropriate number of items, then you have to figure out how to eliminate the ones you don't want, so you find the last one. So how would we do that?
We're trying to do what now?
We're trying to perform the elimination. So we're eliminating every third node.
We could locate it, maybe?
Well, we know it's going to be every third node, so we're not going to be searching for it.
But we would just remove it.
Right. So that's on page 739, removing a node. We'll have a discard pointer that points to the node to be deleted, and then we link around it and delete the one we're discarding. In fact, well, I was going to say we could use the insert head to create a new head, but we're trying to make a circular linked list, so that may not work for us. Alright, so removing a node, you're going to have to figure out how to implement the code for removing a node on page 739. When would you stop eliminating suitors?
When there's only one left.
And how will you know that?
Well, I guess. I mean, if there's 6 and you've eliminated 5, then you know there's only one left.
Okay. In this case, there's an easier way to figuring out when there's only one left. Because it's a circular linked list, what does that mean? What did we say a circular linked list was?
Basically, I guess the way that the elements, the last, I guess,
The last element
it's going to point to, I guess, the first.
Alright, the last element points back to the first element. So if the next element is the same as the current element, that means there's only one element in the list. So if head is equal to item, let's see, if item link is equal to item, those pointers both point to the same thing, that means this is the last item in the list. Make sense? So once your item links back to itself, you know you've eliminated all the other items. And what are the special cases?
I'm sorry?
Do you know what the special cases would be? Alright, well, the things you will have to worry about are if the user says 0, well, you could use that as an ending condition if you want to. If the user says 0, there are no suitors to be evaluated. You can assume the user is ready for you to quit. You don't have to make a linked list or anything. Now, if the user only has one, you're only creating the head, linking it to itself. You have no additional items to join. Technically, you could also just say, oh, well, it's suitor number 1 because there's no other suitors, and you could quit at that point. All the other numbers of suitors will involve creating a head item and some number of other items that you link back to that head in a circular list, and then go through the item, eliminating every third one. Do you have any questions, or you think you can resolve at this point?
So eliminating a node, is that just kind of like calling the delete?
Page 739 has a 3-step process for that. So we find the node that we want to eliminate. And we find the node before that one. Okay. So we have a before and a discard. We then link our before to the link of the discard. Basically, we're linking around the discard node. And finally, we delete the discard node. So in our list, let's see, we would need another pointer. We'll call it, let's call it before. And let's say before points to item. So we say before link equals item link. Okay, so that links around item. And now we can delete item.
Because item is what's being discarded.
Item is what's being discarded, yes. So we'll have to hold on to before and item in order to be able to delete item. So you have to figure out a way to loop through 3 at a time. So let's see. While item link not equal to item, so let's say before equals item, item equals head, item link is not equal to item, or int I equals 0, I less than 3, I plus plus. Before equals item, item equals item link. Okay, this is one way to do it.
So what exactly is this doing?
Well, let's take a look. So we're saying before is equal to the current item. And item equals the next item. And we're going to do that 3 times. Just leave this one off. So after we insert the last item in the list, so the first one is going to be number 1, the next one is going to be number 2, and the next one is going to be number 3, and this before is going to be pointing at number 2. We're then going to link number 2 to number 4, which is the link after number 3, and delete number 3. Make sense? Okay. Now this has a fatal flaw in it, which you're going to need to work out. But that's basically what you need to do in order to solve the problem. Any questions? All right, well, you see what you can do with that, and if you come on a brick wall, let me know and I'll try and get you around it.
Alright.
All right, I guess we'll see you next week.
Alright, I'll see you then.
All right, bye.